Well, as you can see, I've got my diameter across here, and that means that this inscribed angle would be, have its intersected arc as 180, so that would be a 90-degree angle. And what I did was, is I took my compass and I measured the distance across from here to here, which happened just to be convenient, and I made it the same there, and I came up here and made it the same across there, and made it the same this way. So I've got all four sides equal at a square corner, which makes me think that's a square. And we're going to be off and running, and we're going to assume that that is a square. And let's see what we can do with it. I'm going to take the compass again. I'm going to pick a length which I think is relatively convenient, and we're going to measure off a section of the bottom side. Let's label this so we can talk about it better. Let's say once again A, B, C, and D, because we don't have any imagination. And we will measure off a convenient length on the bottom here. Let's say, well, I can see some smudges there on my drawing. I might as well use them. Let's say we go, well, let's go to this one. It's just any old place will do. It doesn't matter, but I have to decide. And I'm going to use that length right there. And I'm going to come over and mark off the same distance over here, this way. So, and then up here again, like this. And then over here on this side, this way. It doesn't matter what this length is, I just want it to be the same on all the sides. So, there's that one. Here's this one here. And you know what? It looks like my compass has been slipping on me, and it doesn't look the same. So I'm going to have to go back and double check it. That's that one there. And this one here. That looks pretty good. And then this one up here. Just slightly off. You know, it seems to be that my compass is moving as I go around. Let me come back here and double check again. That's pretty close. It's over here, there. That's this one here. I hope your equipment's better than mine. There we go. And that's the idea. And then this one here, like so. Boy, is that off. That's a long ways off. It just doesn't look right at all. From here to there, and from here to here. Right there. That's better. Well, we have some mechanical difficulties here, so we can't trust ourselves. Let's see what happens if I connect these points that I've picked this way, and then this way. And then this way. And then here, like so. There. That's interesting. Now remember, we got human error here. We can't guarantee that all of our measurements are working out properly. But I tried to make this one here, let's just call it little a, the same as this one here. And this one here was the same, and this one over here was the same. And let's call this one here that would remain the other side B. And that would make this A and that B. And this one B here, and this one B here. And since this was a square, I've got square corners on each of these intersections here. Like that. And I have a side, an angle, and a side equal to a side, an angle, and a side. which means these are congruent, and likewise these are going to be the same thing. A side, an angle, and a side, an angle, and a side. All four of those triangles are supposed to be exactly the same size. If my equipment was working properly, I think it would look really, really good. Okay, I've got four triangles, and I have in here a figure which I'm not just sure what it is. It might be a square. It certainly looks as though it could be. Let's see here. This angle is 90, and since there's 180 in the triangle, this angle here and this angle up here must add up to 90 degrees. And over here on this side, I would have a pair of angles in the triangle that is equal or congruent to this one. That would be the same. So this one up here, this would match this one there, and this one here would match that one there. So as a result of that, these two must add up to 90, just like these two did. And if I take 90 away from 180, that makes this a square corner in here. There we are. So I'm guaranteed that's a square corner. All right. Well, let's see. All of these triangles were congruent. That means all of these sides were equal. And if that's the case, I'm pretty well positive that the figure in the center there is going to be a square. And since all these triangles are congruent, let's call this side C. And this would also be C, and this would be C, and this would be C here. There we go. We've got a square inside a big square and four triangles. Now what that means is the area of the large square would equal four triangles plus one little square. Alright, the area of the large square would be A plus B times A plus B. That would be A plus B times A plus B, or A plus B to the second power. And the area of one of these triangles would be 1/2 of its base times its height, which happens to be A, and that would be one of the triangles, and I've got four of them. Okay? So if I multiply that by 4, I'll have all the triangles. And I have to add to that the area of the small square on the inside, plus C square. Cool. Well, I need to have somebody who knows how to multiply binomials. And if you might recall, you could do what's called the FOIL method, or if you know the shortcut, you could jump right to it and square that for me. Or if you're not certain of it, you can take and work it out on the side. I'm going to demonstrate quite quickly. If I have 31 and I'm going to multiply that times, I don't know, I'm just going to make this up, say 23. You'd multiply this one times that one, and then this one times that one, 3 and 9, and then you'd move over and you'd move your answer over one space. You'd multiply that times that, and then you'd multiply that times that. You'd add them together, right? Like so. So we're going to do the same thing with this one here, our binomial. We have A plus B, and I'm going to multiply it times A plus B. Alright, multiply this times that. B times B is B to the second power, and B times A would be A and B. Multiplying A times B, I get A and B. Notice I moved over one space. And if I multiply this times that, I get A to the second power. And if I add them up, I get A squared plus 2ABs plus B squared. Let me write that in here. You could have done it other ways and gotten the same answer. A squared plus 2AB plus B squared must equal, well, what's 4 times 1/2? That'd be 2, wouldn't it? That'd be 2, and A times B would be the same thing as B times A, AB, and C squared. Well, I notice 2 ABs on both sides, and if I subtract the 2 ABs from both sides, I will end up with A squared plus B squared is equal to C squared. And that is known as the Pythagorean theorem. But this drawing we have here is not from the ancient Greeks, it's from the ancient Babylonians once again. And when this was discovered by the archaeologist, they had one word underneath that word, and the translation of it was behold. And they had discovered the Pythagorean theorem long before Pythagoras. They didn't have a name for it at that time. We've given Pythagoras credit for his discovery, which occurred later. But the idea is that when you have a right triangle, the two sides squared and added together will equal the long side. A squared plus B squared equals C squared. And that's the Pythagorean theorem, and boy is that useful. There's lots of things you can do with it, particularly if you're in the construction trades and you want to make sure you have a square corner. You can take and measure off a distance here and a distance here and make sure that the squares turn out to be that one squared. And probably the most famous one is the 3, 4, and the 5 right triangle. This would be 3 times 3 is 9, 4 times 4 is 16, and guess what? 5 times 5 is 25, and it works out beautifully. And that was used by the ancient Egyptians with their rope ties and stretching in order to get square corners on such things as pyramids. It's absolutely phenomenal. There are many other combinations of this that also work. That's about all we need to do to this one then. A squared plus B squared equals C squared. It's easy to remember. It's in alphabetical order.